Hello students, this is Mr. Ezra and today we are going to talk about quadratic inequalities. So before we jump into the lesson, I want to kind of spend just a second and tell you that when we talk about quadratic inequalities, really we're talking about a quadratic function, which is a parabolic shape on the coordinate plane. There's an x-axis, there's a y-axis, and we've got this function on there, and the inequality on the graph would have a whole bunch of shaded space, either outside of the parabola or inside the parabola. Today, as we kind of dig into the quadratic inequalities, our solutions are only going to be x values. So we're really only going to be interested in what's true, what the shaded part on the x-axis is for the function. Because of that, we're not going to graph on the coordinate plane every function. We could, and we could look at it that way, but instead, as we're solving these, we're really going to be just focusing in on the x-axis and trying to make sure that we know what the answer looks like in relationship to what x values are possible in the quadratic inequality. So before we do that, let's review some stuff about inequalities that we've seen before this year, we've seen in years past, starting with symbols of inequality, their meaning, and what it would look like on the x-axis if we were to graph them. So remember, this symbol means less than. For example, x less than 4, I would graph with an open circle on the 4 and an arrow to the left. And so you can see less than is almost pointing to the left, isn't it? As an interval, which we want to review interval notation, this arrow to the left means that our interval starts at negative infinity and ends at 4. And because 4 is an open circle, we would use a parentheses on the 4. So that would be the interval representation of that inequality. Less than or equal to has the less than sign and the or equal to sign. For example, x less than equal to negative 5 would be a closed circle on negative 5 with an arrow to the left. As an interval, that would be from negative infinity to negative 5. But the negative 5, because it's shaded, because it is or equal to, would get a bracket. Greater than has the point to the right. It means to the right on a number line. For example, x greater than negative 2 is an open circle on negative 2 with an arrow to the right. This interval starts at negative 2 and goes forever to the right towards positive infinity. And since it's an open circle, since it's just greater than, we make sure that we use the parentheses here. Greater than or equal to is also to the right, but the dot is shaded in because of the or equal to. It's greater than 6 or it's equal to 6. Because of that, the interval is going to start at 6 and go to the right forever towards infinity, but the 6 is included, so it gets a bracket. Today, for the most part, we're going to be using compound inequalities, like the compound and the compound or. So for the compound and, you're going to see things like negative 6 less than equal to x less than equal to 1. We call compound ands intersection problems. And when we have an intersection problem, we're interested in what's shared. Essentially, this is like saying x is greater than equal to negative 6 and x is less than equal to 1. Well, the stuff that's greater than or equal to negative 6 is all that stuff to the right. The stuff that's less than or equal to 1 is all that stuff to the left of 1. And the intersection is what's shared between them. It's just this inside part that's shared. The way that I kind of think about this is on the number line, I'm looking for what's between negative 6 and 1. And the or equal to's with the negative 6 less than or equal to x less than or equal to 1 means that both of those dots are going to be filled in. So as an interval, I'm going from negative 6 to positive 1 with a bracket on both. That's what this compound inequality is going to be as an interval. On the other hand, when we use the word or, when we have a compound or, we call this union. And union is not intersection. It's not what's true for both of them, but instead it's what's true for one or the other or both of them. So since this is less than -2, we have an open circle on the -2, and less than means we shade to the left. Or means this is good, or we could have greater than 4. So that'd be an open circle on the 4 with the shading going to the right. These together are really two different inequalities, or two intervals, I should say, really two intervals. So one of the intervals is from -infinity to -2. The other is from 4 to +infinity. And remember from previous discussions that when we have two intervals that we're unioning together, we use the symbol for union between them, which is just a big U. So it'd be this interval union this interval. A few things to remember as we start talking about inequalities. These are golden rules of inequalities. Whenever you multiply or divide by a negative number on both sides of the inequality, you must change the direction of the inequality. So if I have, let's say, -3x is less than or equal to 12, and I divide both sides by -3, then the direction of the inequality changes as well. So it'd be x is greater than or equal to -4. Even more important in this lesson is if you have to flip-flop across the inequality, or what is on the left you want to move to the right of the inequality, and what's on the right you want to move to the left. When you do that, you also have to change the sign of the inequality. In other words, when you rewrite 9 as less than x, if you want the x on the left, if you want to read it backwards, it's going to be x is greater than 9. If 9 is less than x, then x has to be greater than 9. So whenever we flip-flop around the inequality, the direction of the inequality is going to change to keep the relationship the same as it was. And those are a few things to remember as we get into the problems. Now, here's our first example and some steps that you can use for these examples. Now, as you go through these examples with me, the first step is to change the inequality to an equal sign. Well, I've already done that on all of these questions. The second step is to solve that quadratic equation. We've used several methods for solving quadratics in this class. We've factored, we've used the square root method, we've used the quadratic formula, we've learned how to complete the square. There's a whole bunch of different methods that we can use for solving quadratic equations. In this case, in this video, every one of the questions that we look at, we're going to be factoring because they all are factorable. But I could use another method if I wanted to, or if I had trouble factoring. Now, you'll notice that I have already factored all of the inequalities as we go through. I've changed them to an equal sign and I've factored them. And that's because we've already learned how to factor. I might talk about it really quickly, but I don't want to spend a ton of time for each question factoring and then doing the other stuff, which is the new stuff. So I did the old stuff. I've also already created a number line for you, and I've put the two solutions on that number line. And so what's going to kind of happen is we're going to pick up on these examples at step 5. So you might want to pause the video every once in a while, kind of jot down what I've already done, and then play the video and kind of pick up and add in the new stuff. All right, so question number 1, example number 1. It's already in standard form. Remember, that's x squared plus x minus 12 in this case. Everything's on one side of the equal sign in descending order. Also remember that in standard form for a quadratic, you want the leading coefficient to always be positive. So if it's ever negative, we're going to go across the equal sign and change it. In this case, it looks good. Then we are going to change the inequality to an equal sign like we did. We're going to solve it by factoring. In this case, I got x plus 4 and x minus 3, which gives me a solution of -4 and +3. I want to take these two solutions and put them on a number line and make sure that you put them in the correct order. So -4 should be to the left of 3. On a number line, 0 would be between them, and -4 on the left, 3 on the right. Now, we're going to test 3 values, one from each of the sections that we've just made. You can pick any number between -4 and 3 that you want to. I'm going to test 0. 0 is between -4 and 3, so I'm going to test 0. I've got to pick a number greater than 3. You can use 4, you can use 5, you can use 6, you can use 7, whatever you want. I'm just going to use 4. And you can choose any number less than -4 that you want. I'm just going to choose -5. So I want to test a value from each of these sections, and I'm going to test it in the original inequality. Okay, so I might get my calculator out, and I might say, what is -5 squared plus -5 minus 12? And is that greater than 0? So I'm plugging in -5, I'm testing that value. Well, let's see, that's 25 minus 5 minus 12, and I get 8. Is 8 greater than 0? And the answer is yes, that is a true statement. What that means is that -5 works. When you plug it in, you get something that is true. Okay, we're then going to try 0, something that's in the middle interval. So I'll do 0 squared plus 0 minus 12, and my question is it greater than 0? Well, 0 squared plus 0 minus 12 is -12. Is -12 greater than 0? No. That is false. And since it's false, that means that 0 is not a solution because it doesn't work. Put an X there. And then I might try, or should try, 4. I'll plug in 4. I do 4 squared plus 4 minus 12. And the same question, is that greater than 0 when I plug in 4 for x? Well, 4 squared is 16. 16 plus 4 is 20. And 20 minus 12 is 8. Well, 8, if you can read that, 8 is not greater than, or 8 is greater than 0. That is a true statement. If it's true, it is a solution. So we end up with kind of this situation where things that are to the left of -4 work. If -5 works, then everything to the left of -4 works. Things that are between -4 and 3 do not work. If there's one number that doesn't work, none of them work. And everything to the right of 3 is going to work if 4 works. Since this is a greater than problem, that means that we are going to use open circles on both of those numbers. We only use closed circles for the greater than or equal to, less than or equal to. And when we shade, we're going to shade out to the edges because those are the ones that worked. If you think back to our kind of beginning inequalities, this is an or problem, right? It would be x is less than -5, or x is greater than 4. That's one way to write this answer. One way to write this answer. In interval notation, we would say -infinity to -5 union 3 to infinity. And that would be the interval notation. Those are both correct. One is written as an or statement, one is written in interval notation. Except I did make a little mistake here. That shouldn't be 3. Oh, I did make the mistake there. 3 is correct here. I'm sorry, my mistake is up here. Should not be x greater than 4. It should be x greater than 3. I tested for to know that everything over here works. Now, remember back a minute ago, we said that these are actually parabolas that kind of go through here. And either the outside is shaded or the inside is shaded. So with this parabola, what's happening is the outside is shaded. But we only want to represent the answers on the x-axis. So we're not spending our time looking at the whole graph. We're just kind of focusing on the x-axis and what works and what doesn't to get our answers. In example number 2, same thing. First, I added 16 to both sides to get it in standard form. And then I set it equal to 0. Moved this whole expression to the left side of the equal sign. I really just flip things around the equal sign. Factored x squared minus 10x plus 16 to get x minus 8 times x minus 2 to get two solutions, 8 and 2. On the number line, I put the 2 to the left of the 8, and I'm going to pick 3 numbers to try that are not 2 and 8. Now, I can go ahead and know that since this is greater than or equal to, that 2 and 8 are included as solutions. If you were to plug them in, they would work because it would 2 squared minus 10 times 2 is actually negative 16. 8 squared minus 10 times 8 is negative 16. They are equal. We know that because we solved it. We set it equal and we solved it. Our question is the inside what we shade or the outsides. Is it an intersection problem where the inside is shaded, or is it a union problem where the outsides are shaded? To find that out, we're going to pick a point or a number to the left of 2, between 2 and 8, choose 4, and something greater than 8. We want to choose something that is in each of these intervals, and we want to test them out. And when I test it out, I like to do the original inequality, just so that I make sure that I don't make any mistakes. So I'll plug in 0 first. Negative 16 greater than 0 squared minus 10 times 0. Well, when I plug in 0 for x, 0 squared minus 10 times 0, that reduces to be 0. Is negative 16 greater than 0? It's not. If you end up with a not true statement, that means that this guy did not work. Doesn't work. I'll plug in 4 for x in the original equation. So negative 16 greater than equal to 4 squared minus 10 times 4. And we'll see if this works. 4 squared is 16. 16 minus 40. 16 minus 40 is negative 24. Negative 16 is in fact greater than negative 24. That is a true statement. Since it's a true statement, that means that the middle part is a solution. When we test the number on the right, negative 16 greater than equal to 9 squared minus 10 times 9. The question, is this a true statement? Well, let's do it. 9 squared is 81, and that's 81 minus 90 when you multiply those. So 81 minus 90 is negative 9. Is negative 16 greater than negative 9? Well, negative numbers, they're to the left on a number line, right? So negative 16 is to the left of negative 9, which means it's not greater than negative 9. So that's a false statement. That's a false statement. This one doesn't work. This means that the inside is what is going to be the solution. What's between 2 and 8? This is an intersection problem. So we can say that 2 is less than or equal to x, is less than or equal to 8. That's one way that the answer could be written. Or in interval notation, we would use brackets and say from 2 to 8. That would be another way that the solution could be written. Either one of those would be acceptable. Now we're going to notice something as we move forward. With the way that these quadratics are, we are either shading outside the quadratic or we're shading inside the quadratic. It's one or the other. And that means with these functions the way that they are written, we're either going to have a union problem where we're shading both outsides, or we're going to have an intersection problem where we're only shading the inside. So while it is a good idea to check a number from each of these intervals, if you only check one of the numbers, there's going to be a pattern. It's either going to be check x check or x check x. And really, we can just test one of the numbers to see which of those patterns it's going to be. And from here on out, that's what I'm going to do. It's going to speed things up just a little bit, which is good. So we're at about 20 minutes for the video now, and I still have several problems to work through. All right, so I've already factored number 3. I added 26x to the left to get it in standard form. I noticed there was a common factor of 2, a greatest common factor, so I divided it out to the front. And then I factored the resulting quadratic into x plus 7 and x plus 6, which gave me 2 solutions. When I set x plus 7 equal to 0 and x plus 6 equal to 0, I got these 2 numbers. Now remember, -7 and -6 are our important spots. The fact that it starts as a greater than problem means that they are going to have open circles on them. It's only closed if it's or equal to. We have to test, we really should test all 3 of them just to make sure we don't make a mistake. We have to test one. The easiest number to test is 0. 0 is going to be in this section over here because it's going to go -5, -4, -3, -2, -1, and then 0. And 0 is always the easiest to test. So I'm going to plug 0 into the original inequality. 2 times 0 squared plus 84. And my question is, question mark, is it greater than -26 times 0? Well, I love using 0 because things cancel out quickly. 2 times 0 squared is 0. 0 plus 84 is 84. And then -26 times 0 is 0. And the question is 84 greater than 0? And the answer is yes. That is a true statement. It is greater than. Since that is the case, the pattern is going to have a check out here, which means it has to have an X in the middle and a check over here. It has to be shaded on the outside of the quadratic. Essentially, I'm looking at a union situation here. Okay. Remember, there are 2 ways that we can write this answer. We either write it with the word or. We would say that x is less than -7 or x is greater than -6. That's a perfectly good way to represent this inequality that we've shaded here. The other way is to use interval notation by saying -infinity to -7 is one of the intervals. I'm going to union that with -6 to +infinity. And that is another great way to represent the answer to this inequality. Okay, but then move on to number 4. Again, I've already put it in standard form. Standard form or factoring requires that you have a positive leading coefficient. So to get this x squared to be positive instead of negative, I added and subtracted everything across the equal sign. So pretend that this is an equal sign. We're changing it to an equal sign. I added x squared. I subtracted 2x. I subtracted 3 to the other side of the equal sign. So that gives me a quadratic that I actually can factor. And once I factored it, I got x equals 3 and -1. The -1 is less than 3, so it goes on the left. Now, in these numbers, where is 0? 0 is in between these two, right? So that's the one I'm going to test. It's the easiest to test. I'm going to come off to the side, and I'm going to use this original inequality and say, is 0 greater than or equal to, question mark, is it greater than or equal to negative 0 squared plus 2 times 0 plus 3? Well, negative 0 squared is 0, 2 times 0 is 0, 0 plus 0 plus 3 is 3. Is 0 greater than 3? No, that's a false statement. 0 is not greater than 3. 0 is less than 3. So since that's the case, since that's a false statement, that means that the inside, this interval here, does not work. The pattern must be that the outside is what we're shading. We're shading to the left of -1 and to the right of 3. Do we use open or closed circles on the -1 and the 3? Because it's greater than or equal to. We know that these are going to give us equal to, so we are going to include them with actual dots. So we can write it as x less than or equal to -1, or x greater than equal to 3. That's a good way to write that answer. Or in interval notation, we would say from -infinity to -1 with a bracket on the -1, or from 3 to infinity with a bracket on 3. Either way would be a good way to write. Wow, so we're about 25 minutes right now in the video, and I've got 3 more problems, so I probably need to speed up just a little bit. I have factored this guy, and I ended up with a fraction because the leading coefficient was greater than 1. I ended up with 2x plus 5 and x minus 1, which gave me these two solutions. 0 is going to be between them, so I'm going to test 0 in the original inequality to see if it works. Now, I'm going to speed things up just a little bit. Whenever I plug in 0 and I multiply or raise 0 to a power, it's always 0. So this is essentially going to be 2 times 0 squared plus 3 times 0. That's just 0. My question is 0 greater than or equal to 5. Is that true or is that false? Does this number work? Well, 0 is not greater than or equal to 5. That's false. And since it's false, that means that 0 is not a solution, which means that nothing in the middle is a solution. And we have another situation where the outsides are what would work. And I'm not doing this because it takes some time. But if you were to test 2, 2 times 2 squared plus 3 times 2 is going to be greater than 5. It's going to work. It's going to be true. But remember that or equal to means we use closed circles on those two special numbers, those two special spots. And now we need to write it as either in terms of x or as an interval. So in terms of x, we'd say x less than equal to -5/2, or x greater than equal to 1. In interval notation, -infinity to -5/2, union, oops, that should be a bracket, shouldn't it? If anybody caught that, good catch. So that's a closed circle. This should be a bracket here. And we've also got a closed circle over here and a greater than or equal to, so that should also be a bracket on the 1. Now, why am I showing you 2 different ways to write this? Well, I don't really care on an open response which one of these you give me because they're both correct. Well, let's say you're taking a Moodle quiz and it's multiple choice. I don't know what I'm going to put in that multiple choice options. It could look like this. It could look like that. You should be comfortable with either. So I just want to show you both, just in case. Number 6. Let's say that we've already factored this. You can look at my work and see that hopefully I correctly got 2 and 4. I want to test 0 because it's the easiest thing to test. 0 is to the left of 2. It's over here somewhere. 0, 1, and then 2. When I plug 0 in, remember I can do this really fast because 0 is awesome. -2 times 0 squared plus 12 times 0 is 0. So my question that I'm really asking when I plug in 0 is 0 less than or equal to question mark 16? And in fact, that is a true statement. Yes, 0 is less than 16. What does that mean? It means that this interval is good, and it's always a pattern of check, no good, check. Good over here, no good in the middle, good over here. We have another OR problem. We go back to the original inequality and see that it's or equal to, that's closed circles, closed circles. So x is less than or equal to 2, or x is greater than or equal to 4. The alternative way to write that is negative infinity, comma 2, union 4, comma infinity. All right, question number 7. I've already factored. I got 1/3 and -1. I put them on a number line. I want to test 0 because it's the easiest to test. On the number line, 0 is going to be in the middle here between -1 and +1/3. When I plug it in, 3 times 0 squared plus 2 times 0 is 0. And 0 minus 1 is -1. And the question that I'm asking myself is -1 less than or equal to 0. Is that a true statement? And it is, in fact, true. All negative numbers are less than 0. So what does that mean? It means that the inside is shaded. This pattern is x, check, x. The inside is the good part here. It's going to be less than or equal to, so the or equal to lets us know that these points are included on the number line. And this is an and problem or an intersection problem where we're saying one way to write it is -1 less than equal to x less than equal to 1/3. Perfectly good way to write that. Or in interval notation, we can just say from -1 to 1/3 with brackets on both sides because the points are included. Our last example of inequalities here, again, I set it equal to 0. I added 2 across so that it's in standard form. Leading coefficient is greater than 1, but I figured out the factors and got -1/2 and -2 as the two solutions. Put those on a number line. -2 is less than -1/2. Bigger negative numbers go to the left, right? And when I'm looking at these numbers, where is 0 going to fall? That's the number I'm going to test. Well, 0 is to the right. All negative numbers are less than 0. 0 is going to be to the right of these two numbers. It's over here somewhere to the right of -1/2. So when I test 0, I want to know, does it work or does it not work? Well, I can just plug it in. 2 times 0 squared is 0, plus 5 times 0 is 0. So the left side of my inequality that I'm checking is 0. And I want to know, question mark, is 0 less than or equal to -2? When I plug in 0, do I get a true statement? Well, 0 is not less than -2. That is a false statement. So when you test it and you end up with a false statement, it doesn't work. There's a pattern that must happen here. And it's either check x check or x check x. Well, if there's an x on the right interval, that means there's a check in the middle. If you were to plug in like -1, it would be true. It would work. I promise. You can try it out if you want to. The or equal to, less than or equal to, means instead of an open circle, we include those two numbers because it's also equal to. And this is a compound inequality that's an intersection problem where we would say that all the solutions are between -2 and -1/2 inclusive, meaning -2 less than equal to x, less than equal to -1/2. The alternative way to write that is an interval notation. We would just say bracket -2, comma, -1/2. These intervals are always in order from least to greatest. Well, that is it for the examples today. Before we get to the close, there is something I want to point out, and I know it's just going to take another second, but let's suppose that we had a coordinate plane. I'm actually going to draw two of them, right? And I want to point out that there are some things that we're not talking about that could happen. And if they were to happen, then what we're doing would look just a little bit different. You know that there are sometimes quadratics that don't have, we can't factor, so they don't have real solutions. They might end up with imaginary solutions. And on the graph, what that means is that the function is kind of off in space here. Well, if the parabola is off in space, and our answers are, we want to know what's true along the x-axis. In this case, if the inside of the parabola were the shaded part, our entire x-axis would be not shaded, which means there would be no solution. And that is a possibility. You can have one of these guys with no solution. Or if the outside of that parabola was shaded. Even though the function doesn't cross the x-axis, every single number along the x-axis would be true. It would all work for the inequality. And in that case, the solution would be all real numbers. So those are two distinct possibilities when the function doesn't touch the x-axis. It can be either no solution or it can be all real numbers. On the other hand, let's say that the function does touch the x-axis, but it only touches it in one spot. It only intersects it in one location. Well, think about this. If we are shading inside, if it is a solid line, if there is a dot here, the only truth is going to be that dot. That number is the only solution. But if instead this were a dashed line, well, let me take away, this were a dashed line. That would mean that this solution is not included because it would be a just less than or just greater than, and we would have no solution here. Also, if this were shaded on the outside, if this were a full less than or equal to, greater than or equal to, this point's included, we're at all real numbers again. Or if this were a dashed line, or a dashed function, I should say. In other words, if it's less than equal to or greater than or equal to, well, this point wouldn't be included because the function itself wouldn't be included. And our solution would be all real numbers except for that one spot where it intersects. And I'm not trying to confuse you. I know some of you are going, well, why are you telling me all this? Well, I'm not trying to confuse you. I just want you to know that we really focused on a particular type of question today where there were two real solutions and everything was factorable. There are other cases out there that exist, and when you come across them, you get different types of solutions than the ones we saw in the notes today. I hope that you made it through all of these notes. I know that this was another long video, but I thought rather than breaking this up into two separate videos, I'd just put it together and see how things went. Quadratic inequalities is something that you're using things like factoring that you're hopefully good at by now. You're just adding some new steps of thinking about what it would look like on the x-axis or the number line. What solutions for x would make it true? And we will get some practice in class, have some Moodle quizzes. It will be awesome. I will see you then. See you in class.